Alright, so the next two examples are going to be where we have capacitors that are both in series and parallel combinations. And with these, it takes some work to really kind of visualize what's going on and where you should start. There's no, you have to start with the ones in series or you have to start with the ones in parallel. You really have to just look at the circuit and go, alright, I need to start this one this way to simplify this little branch. And so if we look here in this example, C1 is 9, C2 is 4, and C3 is 4 microfarads. And we have C1 and C2, these two are in series, and this combination here is in parallel with C3. And so when you look at this, right, we have to say, well, where do I start? And we always want to think, how can we simplify it so that the next step is going to be easier? And so if we look here, I'm going to take these two and I'm going to combine those first, because then our circuit becomes this. Right? And so we have two parallel capacitors where this one here is C12. Let me redraw that. C12, and here's C3. And so we're going to find C12. And so C12 is going to be equal to 1 over C12, because again they're in series, so that's 1 over 9 plus 1 over 4. And so if we get a calculator and figure that out, we get 1. We'll get 13 over 36, but again we want to take the reciprocal of that, and so C12 is equal to roughly 2.8 microfarads. And so now this combination can be used or created with using just two capacitors, where this here is still 4 microfarads. And here we have now 2.8 microfarads. And so this combination can be made into just one capacitor by using the parallel combination here. And if you remember with parallel capacitors, so C123 is just going to be C12 plus C3. And so we're going to get 2.8 plus 4. And we get 6.8 microfarads. And so our C equivalent is 6.8 microfarads. Okay? And so this was an easy one because we were just looking for the capacitance. They didn't ask us to find anything else. But again, we're going to look and see like what's going to make simplifying this easier. In this case, we want to start with this series combination here and then work with the parallel on this combination to get our equivalent of 6.8 microfarads. All right, and so let's look at the next example. Here we have C1, C2, C3. We have C1 parallel with C2, and that combination is in series with C3. And so we want to first find the equivalent capacitance, find the total charge in the system, find the potential across each capacitor, and then find the charge on each capacitor. And so we're going to start by looking at our circuit and figuring out like what can we simplify first. And so again, we have C1, C2 that are in parallel, and that's in a combination in series with C3. And so when I see this, right, I would think to combine C1 and C2. I can't really do anything with C3 until I make an equivalent capacitor there. And so I'm going to draw C12, C3, and we know that for capacitors in parallel, we're just going to add the values. And so C12 is going to be C1 plus C2, and so we get 17.3 microfarads. And C3 is still 4.5 microfarads. Now, this combination, right, we combine C1 and C2, which are in parallel. We now have C12 in series with C3, and so this will give us a new circuit with just one capacitor. And if we want to find C1, 2, 3, right, well, we have to use the 1 over C equivalent equals 1 over 17.3 plus 1 over 4.5. And so if we type that into the calculator and then take the inverse of our answer, we'll get roughly 3.6 microfarads. And so the equivalent capacitance here for our 3 capacitor system is 3.6 microfarads. So now that we know that, we can find the charge on our equivalent capacitor. So Q equivalent will equal C equivalent times the potential, and so the potential, it tells us, is 12.5, and so we'll get 3.6 times 12.5, and so Q equivalent, so the total charge of the system, is 45 microcoulombs. And so I know that here we have 45 microcoulombs. And so this answers A and B. The equivalent capacitance is 3.6 microfarads, and the total charge in the system is 45 microcoulombs. And so for C and D, we're going to work backwards to find the total charge and the potential across each capacitor. And so to find either of those, we're going to, again, work our way backwards. And so we found C equivalent, and we found the total charge. The previous diagram, our 2 capacitor system, is in series, which means that the potential across C12 plus the potential across C3 is going to equal it's going to be 12.5 volts. And I know the charge on each of these has to be the same as what we found on our equivalent, because we went from our equivalent to 2 series capacitors. And so Q12 is going to be 45 microcoulombs, which is going to equal Q3. And so since we now know how much charge is on each of these, we can find the voltage across each of these capacitors. So V across 3 is going to be Q3 over C3, and so that's going to be 45 microcoulombs, and C3 has a value of 4.5 microfarads, and so we'll get 10 volts. And so if we were to put a voltmeter across here, right, it would register 12.5 volts. Oh, I'm sorry, not 12.5 volts, 10 volts. That's what we just found. For C12, even though this is a combination of 2 capacitors, if we replace those 2 capacitors, C1 and C2, with this equivalent, well, its total charge will be 45 microcoulombs, and its potential is going to be Q12 over C12, and so we'll have 45 microcoulombs over 17.3, and we'll get 2.5 volts. And so if we put a voltmeter across here, we would get 2.5 volts. And again, that makes sense since the sum of my potentials across each of these capacitors in series has to equal the total potential. And so we get 12.5 volts. And so now we found the information about C3, right? We found the potential to be 10 volts, and we found the total charge to be 45 microcoulombs. The last thing we need to do is find the charge and potential across C1 and C2. And so I'll do that over here. And what's going to help us is the fact that, well, if there's 2.5 volts across C12, well, then I know from A to B, again, if we were to insert a voltmeter, we would get 2.5 volts. And so that tells me that V1 equals V2, so the potential across the first capacitor is equal to the potential across the second capacitor, which is equal to that 2.5 volts. And so to find the total charge, we're going to say Q1 equals C1, which is 12 microfarads, times 2.5 volts. And so Q1 will equal 30 microcoulombs. And so to find Q2, well, Q2 is just going to be C2 times V, 1, 2, right? The potential across 1, 2. And so we get 5.3 microfarads times 2.5 volts, and we should get 15 microcoulombs. And again, that makes sense since the sum of the charge on C1 and C2 has to equal the charge on C12, and so 30 plus 15 gives me that 45 microcoulombs. And so again, this is kind of messy, I apologize for that, but we're going to work forwards to get that equivalent capacitor, and then once we find that, we work our way backwards to find all the information about the other capacitors.